We're going to look at how we can use bond energies as a third alternative way of finding the enthalpy change for a chemical reaction. So in this example, here's the reaction that's occurring. Hydrogen gas and fluorine gas are going to react with each other to form hydrogen fluoride. If you remember from Dalton's atomic theory, one of his key components of that theory was that chemical reactions involve taking apart the atoms that were forming the molecules of the compounds that are going to react. So we're going to pull all the atoms apart. As they're randomly moving about, they'll start to interact with each other and they'll form new bonds. So it takes energy to pull them apart. That's endothermic. And energy arises or is expelled when new bonds are formed, and of course that means it's exothermic. So here is the little formula that we're going to use. So the heat of reaction is equal to the summation of all the energy to break all of the bonds of the reactants minus the summation of all of the energy that is emitted or evolves when new bonds are formed in the products. So you're going to have to reference your bond energies table to help you solve these problems. Let's start with the reactants. And the first reactant, obviously the hydrogen molecule. It's made up of two atoms, but there's only one bond to contend with. I generally put a label above the numbers so I know which bond I'm dealing with. I looked up on my table the bond energy for a hydrogen-hydrogen single bond, which is 432. Then I go to the fluorine, and again, I only have one bond, and the bond energy for a fluorine-fluorine single bond is 154 kilojoules. So when I add those up, that'll be the energy that had to be put into the system to break those atoms apart. Now let's go to the product, and I've got two hydrogen fluoride molecules forming. In each molecule there is only one bond, hydrogen fluorine single bond, which I looked up and found was 565. Now I'm going to add up everything in the first bracket. I get my products first, 432 plus 154. I get the product of my second bracket, 1130 kilojoules will be emitted. Add up that first bracket, and of course I see I am going to evolve more energy than I ever had to put in, so clearly this is an exothermic reaction, and the enthalpy of reaction, or the heat of reaction, is negative 544 kilojoules.